So hello everyone, welcome to this online video on Newton-Raphson load flow. In the previous lecture, we had seen brief introduction to it, but then again, uh, we'll try to solve one full-blown load flow problem using Newton-Raphson method. So I'll also review everything so you don't miss the previous one. So let's get started. So I'll just briefly explain you what is the method. So the Newton-Raphson method is for solving functions which are of the form f of x equal to 0. So if there is a nonlinear function f of x and the value is 0, and then you want to find what is x. Now you might ask a question before we continue, that what if I have f of x equals some number. So let's say there's some other function h of x equal to b. Now can you apply Newton-Raphson for this? So the answer is yes. So what you do is you take the h of x to the right side and define a new function, something like g of x equal to b minus h of x. This value will be 0, so therefore now I am getting g of x equal to 0, and then I solve this. So the solution of g of x is nothing but same as the solution of h of x. So basically it is not required that always it should be 0. You can also apply in the case of h of x equal to b. So can also be applied. So this is NR method. Can also be applied if RHS right hand side is not equal to 0. So this is the example for this. So anyway, this is a side point. So I just put a box out on this. So whenever you have a function, nonlinear function, you want to solve it, then you can define. So this is by defining g of x. So you want to solve a function f of x equal to 0, use Newton-Raphson method. So solve using NR method. So if the function is nonlinear function, how you're going to solve it? So that is what is the question. I'll also give you a couple of examples and then we'll solve it. So as I've already explained, so let me just reiterate it. So the NR method. So NR method makes use of the fact that we have the function. If I differentiate a function, so let's say I have a function f of x. Now I differentiate this function with respect to the variable x. So this is approximately equal to, so that's why this is approximately equal to symbol. So approximately equal to delta f by delta x, and where limit delta x tends to 0. In fact, the more closer this delta x equal to 0, then this more accurate this becomes. The differentiation of a function is nothing but change in the value of function with respect to change in the value of the variable. This already you know. This is nothing very difficult here to see. So I'll write once again like this: df of x by dx is equal to, now f of x. What I want to do is I'll write it f of x1 minus f of x0. So x0 is present value of x, and then x1 is next value of x. So therefore x2, x3 could be subsequent values of x. Now assume that x1 itself is the, so assume x1 is the solution, but x1 is unknown. So that's what we want to find out. So what is the meaning of x1 is the solution? That means f of x1 equal to 0. So this is known. So this is a side point. So let's continue here. So the numerator will be like this, and the denominator will be x1 by x0 naturally, because if I substitute x0, I get this value of function. If I substitute x1, I get this value of function. This is delta f and this is delta x. As I said, x0 is already known because it is our present value. x1 is unknown. So from this, I want to solve what is x1. So how to solve what is x1? So just take this to the other side. So I get next step like this. So from above, find x1. So the x1 is something like this. x1 minus x0 equal to f of x1 minus f of x0 divided by d of x0 by d of x0. So this differentiation of the function at the location x0, and then this is what is there. I basically, this term I brought it to the denominator here, and this term I brought it to the numerator here. So nothing difficult here. And this value already I know f of x1 is 0. So therefore I'll write x1 is nothing but x0 minus f of x0 divided by df of x0 by d of x0. So I take the function value, then divide it by the differentiation of the function value, and then subtract it from the existing value of x. So I get the new value of x. So this is the Newton-Raphson method. So if I generalize it, by generalizing, xn plus 1 is equal to xn minus f of xn divided by d by dxn of f of xn. So basically this is otherwise let me write it something like this, f dash of xn. So this is the generalization of the Newton-Raphson method. So this method you can use it to solve any nonlinear function. Only the condition is that your xn needs to be close to xn plus 1. So if you know the vicinity or if you know the solution to a reasonable approximation, then you can find the solution by doing this iterative method. So if you iterate it, so since this is not exactly equal, so here I am saying almost equal. So in one iteration you will not get solution, you have to do multiple iterations. So let's take one example function and then let's solve it. Now for solving this example function, I will take one famous example from electrical engineering, that is the model of a solar cell. So I'll take a very simplistic and very idealistic model, that is there is a current source and then there is an anti-parallel diode, and current source anti-parallel diode, this itself is my simple lossless solar cell. This whole thing is the model for solar cell. And then as a load, I just connect a resistor. So let me also consider the values also. So I mark, so this one is the photocurrent, so IPH I say, and this one is the diode current, ID I'll say, and this one is the output current, that is IPV, so the output of the PV cell. And here the voltage VPV is what is the voltage generated and IPV is the current generated, and the power generated will be VPV into IPV or IPV square into R. Now IPH itself is proportional to the amount of solar radiation. So this is solar insolation, ISO. So I'll give the equations for this. So IPH is nothing but proportional to the isolation. And let's assume for 1000 watts per meter square of isolation, current is, so that is IPH current is 10 amperes. So this is just an assumption. So I'm as you see, the whole point is to explain Newton-Raphson method. So don't worry about the in-depth details of the solar cell. This is just an equation, you can consider it. So I can write IPH is nothing but this is isolation. So ISO isolation multiplied by 10 by 100. So if the isolation is 1000, then 1000 will cancel and then I'll get the ampere. So this 10 by 100 is my constant of proportionality. So this is equation 1. Now equation 2 is nothing but your diode current. So the diode current will be proportional to this, will be according to function of this voltage. So ID is nothing but Is e to the power of Vd by n into Vt minus 1. So this is a standard model for a diode current ID. You might have seen this in one of the diodes textbooks. Let me explain the terms here. So n is, typically its a value is 1.2. This is nothing but ideality factor. And then Vt is nothing but 26 millivolts. This is nothing but thermal voltage of a diode. So again, don't worry about the technicalities of this. The point is not of this course now to explain the solar cell. The point is to explain an equation in which we require Newton-Raphson method. So Is is nothing but reverse saturation current, and typically the value will be 10 to the power of minus 12 amperes. So it is very low current. So this is this one, and e to the power, and then this is 1. So I think everything I have defined to calculate what is ID as a function of Vd. So now, sorry, this Vd is nothing but the voltage of diode, but then I have given VPV as a notation. So let me change it as a VPV. So finally now, what is the IPV? IPV is nothing but IPH minus ID. So you look here, ID current is, at this point if I apply Kirchhoff's current law, total current is IPH minus ID is nothing but IPV. But IPV multiplied by R is nothing but VPV. So VPV equal to IPV into R. So this implies that IPH minus ID whole into R. Or in other words, I want to write what is the value of IPV. So this implies that IPV equal to R by VPV. So this I'll substitute back into this equation. So I'll get IPH minus ID equal to R by VPV. So here, if I substitute again the value of the above things, so isolation, the amount of isolation, ISO, into 10 by 100, okay, minus diode current is nothing but 10 to the power of minus 12 e to the power of minus VPV divided by n into, so n already I know, that is 1.2 into 26 milli. So 26 millivolts means 0.026. Okay, and then minus 1 is equal to R. Let's take R equal to 5 ohms divided by VPV. So now you see this is one full equation. So let's say initially my isolation is 800 watts per let ISO equal to 800 watts per meter square and R equal to 5 ohms. So if I make these assumptions, then so this will be 800 into 10 by 1000. So this will be 8 amperes. So 8 minus 10 to the power of minus 12 e to the power of minus VPV divided by, so what is 1.2 into, let me just keep it as it is, 0.026 minus 1 minus 5 by VPV equal to 0. So this is in the form of, f of VPV equal to 0. Solve it. So the question is, what value of VPV will satisfy this equation? So it is little difficult to solve straightforward way. because it involves e to the power and all these things. So imagine that I give you this equation and then ask you to solve. Find the value of VPV which satisfies this equation. So forget about all the now theory which I explained above. I just look at this equation that is there on your screen. Now you want to solve this. In fact, to keep it more generalized, I'll say I'll just replace this with x. Just solve 8 minus 10 power minus 12 e to the power of x by 1.2 into 0.026 minus 1 minus 5 by x equal to 0. So somebody has given you this equation and asked you to find the value of x. So this is my f of x. F of x equal to 0, solve it. So now the solution is nothing but use NR method. So in my next video, I'll explain how to use Newton-Raphson method to solve this particular equation. Thank you. Okay, so now we have this function and then I want to solve using Newton-Raphson method. So what is a general expression for solution of Newton-Raphson method? Already we had written it in my previous video. That is xn plus 1 is equal to xn minus f of xn divided by f dash of xn. So first what I need to do is find out the f dash of x. So differentiate this function that is there above with respect to x. So differentiation of 8 is 0. Then we have x here, so I'll get minus 10 to the power of 12 here. Then e to the power of x differentiation is e to the power of x. So it is same thing, x by 1.2 into 0.026. Then differentiation of minus 1 will be 0, so although it is multiplied here. And then this one, x also has this factor, so I have to multiply it with, or I have to divide the entire thing with 1.2 into 0.026. So this is the differentiation of this term. I also have another term minus 5 by x. So what is the differentiation of minus 5 by x? So that is x to the power of minus 1. So it will become minus 5 by x square. So this is the differentiation of this term. So this entire is the function differentiation of the f dash x. So I have f of x, I have f dash x. So I have everything sufficient. So just assume that x0 is 1 and then I want to solve it. So how to solve it? So nothing but x1 equal to x0 minus f of x by f dash x. So to solve this, I'll take use of my MATLAB interface. So let me switch over to MATLAB interface. So on your screen, now you're able to see my interface. So on the left, I can write my code, and on the right side, when I execute the code, I'll be getting the result of that code. So let's do this. So here, so first line, I'm just clearing all the variables and then clearing it. Let me just save this nr solar. Okay, now I think there's a problem with the software. Let me just open it. Okay, so I'll be using my MATLAB interface for doing this. So let me go to that interface. So this is the place where I'm writing the code. So first is I'll begin by defining my initial value. So initial value of x is 1. So this is my initial value. Next is I want to set up a for loop. So for m equal to 1 to 5. So I'll run this loop 5 times. So basically I'm performing the Newton-Raphson iterations for the 5 times. So here first I will define what is my f of x. Then I'll define f dash of x. So 2 functions I have to define. So what is f of x? So if I just go back to my screen, so if I go up, this is the f of x as given in the screen. So that is, I'll just enter that 8 minus 10 to the power of minus 12, then e to the power of x by this. So then e x p x divided by 1.2 into 0.026. So this whole thing minus 1 will be, this entire thing will be my diode current. So minus, so instead of phi by x, so I'll write r by x and then I'll define my resistance. So let's define the resistance. R equal to 5 ohms. Similarly, my isolation also I'll define. So 800 watts per centimeter. These are basically, this is the load resistance and this is my solar insulation. So accordingly, I'll just change this formula here. So this will be ISO into 10 by 1000. So this was my equation before. Now once I have this, the next step, okay, it's not stretching more than that. Okay, the next step is to differentiate this function with respect to x. So this is a constant, so there's nothing here. So I have minus 10 to the power of minus 12. So here I have to give multiplication symbol multiplied by exp. So differentiation of e to the power of x is same. So I'll just copy the same. Then later that minus 1 will not be there. So I can just close the exponent. And then I have to divide it by 1.2 into 0.026. So basically I'm just giving the value of f dash x. Then minus, I have r by x here. So differentiation of r by x is minus r by x square. Because differentiation of 1 by x is, oh, I think this will become plus. So differentiation of 1 by x is minus 1 by x square. So that minus into minus will become plus. So this is my entire function f dash x. So now I have f dash x and I have f of x. So what is my new value of x? X minus fx by f dx. That's all. So this is my Newton transform. So if I do this 5 times, then I can get the value of x. So let me just display the value of this. So if everything is correct, we'll be able to see the solution on the right side of your screen. So let me just execute it and see. So there is some syntax error. Obviously, as I expected, it is in line number 11. So let's see. 10 to the power of minus 12 into so whether all the open brackets are closed or not is what I'm checking. So let me just take a pause here. I'll check the error and then come back. Okay, so I have figured out where the problem was. The problem was in this line. There was just a matching of brackets, opening and closing brackets was a problem. So I have just figured it out. Uh, Another thing I had to correct myself is this will be plus phi x, because if I differentiate phi by x, so it will become x to the power of like 1 by x to the power of minus 2, and then the minus sign will also get cancelled, so it will become plus. So this is plus 5x. So anyway, I have now f dash x, and then I have f of x. So in line number 9, f of x I have defined, and line number 10, f dash x I have defined. So you can just pause the video, and then you can also refer to the equation which I have written here. So from this, line number 11 here, you can see the Newton-Raphson method, x minus f of x by f dash x. So now, if I run this 5 times, I'll get 5 successive values of this function. So like this, on the right side, you can see I'm starting with 0.96987. In fact, the initial value was 1. So this is the initial value. Let me display that also. So initial value was 1 on the right, you can see. Then it becomes, gradually it changes, and then finally it settles to this. Of course, in the third decimal is what it's changing here. So let's run it a couple of more times. Instead of 5 times, let's say I'm running it 7 times, this Newton-Raphson load flow. So then I'm getting final value as 889009. 0.88909. So this is the voltage. So what is the power output of the solar cell? So to know the power output, I can just simply use, first I'll find the IPV. So IPV is nothing but VPV by R. So we have done this before. And then the PPV, the power output of the voltage, this thing. So PPV is nothing but, so basically VPV is a variable which I earlier replaced with X. So now I'm just equating with X. And then VPV into IPV. So now when I run this, sorry. So now when I run this code, I'm able to see the IPV and PPV. So 0.158 watts of power. So it's not very high power. So let's reduce the resistance and see what happens. Instead of 5, I'll use 4. So now if I run, the power output increased to 0.2 watts. So similarly, if I keep reducing it, so let's say I give 3. So then again, if I run it, the power output is 0.276. So like this, for different values of R, I can know what is the power output. So now if I give further reduce R equal to 2, again I run it. So power output is further increased. So this means the lower the value of R, the higher is the power. But then that always not the case. Sometimes it will be there. So for example, if I give very small value for R, so then of course here again very high value is coming. We need to check that. So in any case, what we are seeing is how you can use a Newton-Raphson method to solve a problem successively and then find a solution, something like this. So if R is 1 ohm, so then I am getting 0.92242. Okay, so now let's apply this for a 2-bus system and see how Newton-Raphson method can be used to solve a 2-bus system. Let's continue our analysis, and I'll apply this method for a 2-bus system and then see how it will be done. In fact, we had already solved this problem in one earlier example. So, but then in the last moment you could not finish the problem. So I thought I'll once again take it up and then I'll explain step by step and then we'll finish the problem. So Newton-Raphson for 2-bus load flow. Now in a 2-bus system, it is very basic. So let me explain the system. The system is having bus 2 with a load of 1.0 plus j 0.5. So this is the per unit load. And the impedance of the line is j 0.05. So this is the reactance of the line. So the admittance of the line will be minus j20. So just the reciprocal of this. This is bus number 1, and the bus number 1 has a generator, and this is typically V1 delta 1 equal to 1 angle 0 degrees. So this is basically the slack bus, which means I already know what is the V1 and delta 1. The only thing that is unknown is V2 delta 2, and that is what we want to find out. So find out V2 delta 2. And once you know what is V2 delta 2, I can find out what is the current in the line 1 2, what is the power flow in the line 1 2, and so on. Okay, so let's get started. What we need is we need for defining two unknowns. I need two equations. We have two unknowns, so we need two functions. So how to do that is, first let's order the unknowns. Order the unknowns. So how to order the unknowns? Deltas first and followed by V's. So we have unknown x equal to delta 2 followed by V2. So we are solving both of them together. Once I have the unknowns, then I have functions. So wherever you have delta, replace it with the power, and wherever you have voltage, replace it with the Q. That's all. So these are the functions. So you know, we had derived it several times, the load flow expressions. So what is P2? So P2 is nothing but summation I equal to 1 to n, where n is the number of buses in the system. So y to I, Vi, V2 conjugate cos of theta 2i plus delta I minus delta k. This this is the standard power flow equation. Similarly, what is Q2? It will be exactly the same with a minus sign at the beginning and cos replaced by sine. So this we had derived it before. I'm just copying from the above, and then this will be the sine. Now I have two functions, P2 equal to something and Q2 equal to something. These are the two functions that I'm going to use for solving the unknowns. So let's, for a two bus system, n equal to 2, so let's write it for two bus system. So for two bus system, what is P2? So just look above. So here in the place of I can put 1 and 2. So that way. So I'll get two terms. So this will be y21, v1, v2. So this conjugate will not be there. I'm sorry. Because we are just taking the magnitudes of all these things. So basically these are all absolute values. So P2 is y21, v1, v2. Then I have cos of theta 21 plus delta 1 minus delta 2. This is a one term. Another term will be y22 v2 square cos of theta 21, theta 22, and then this delta delta will cancel, delta 2 minus delta 2 will cancel each other. So this is my expression for v2. And if I further simplify, if you look at our network, so if you look at our network, let's draw the y bus for our network. It will be a 2 by 2 y bus network, and this will be J20, this will be J20, this will be minus J20, and this will be minus J20. And the angle, the magnitude is 20, the angle is minus J, that means minus 90 degrees. So if that is for the Y22. So Y22 is 20 angle minus 90 degrees. So if I come down, so here theta 22 is minus 90 degrees. Cos of minus 90 degrees is 0. So this entire term will equal to 0. So finally I have a function P2 is equal to y21 v1 v2 cos of theta 21 plus delta 1 minus delta 2. So this is equation number 1. Similarly, what is Q2? Q2 will be minus y21 v1 v2 cos of this is not cos, it will be sine of theta 21 plus delta 1 minus delta 2 minus y22 v2 square sine of theta 21, sorry, theta 22. Now, theta 22 is, as you see, minus 90 degrees. So, sine of minus 90 degrees is minus 1. So, this will become minus 1 into something. So, this will become plus. So, finally, I have Q2 equal to minus y21 v1 v2 sine of theta 21 plus delta 1 minus delta 2 plus y22 v2 square. So, this is my second equation. So, I have two equations. Now, I want to solve them. So let me clearly write down these two equations also. In fact, what I'll do, I'll take this P2 onto the right hand side and then I'll make it 0 equal to something. So I'll say function P2 is equal to 0, which is equal. So this is function. Actually, P2 is not, P2 is the name of the function. The variables are V2 and delta 2. Okay, so this is equal to y21 v1 v2 cos of theta 21 plus delta 1 minus delta 2. So this is, of course, minus P2 will be there. So this is first equation. Then function Q2 is again value is 0. That will be minus 21 V1 V2 sine of theta 21 plus delta 1 minus delta 2. Then I have another term plus Y22 V2 square minus Q2. So I have two functions. So let's differentiate them. Differentiation of FP2. Now there are two variables. So I have two functions. So this is called my Jacobian matrix. Sorry. This is called my Jacobian matrix. I have two functions. So the function is function of P2 and the function of Q2. And then this is the variable is delta 2 and the variable is V2. So here I will say differentiate function P2 with respect to delta 2. Here differentiate function P2 with reference to voltage V2. Differentiate function Q2 with respect to delta 2 and differentiate V2 with respect to, sorry, this is function P2, function Q2 with respect to V2. So all four combinations we are getting here. So let's do this differentiation. So, okay, so I think I need to recopy this. I'll just copy this and then paste it again. Here. Now let me get the Jacobian elements. So my J equal to, so first I'll differentiate the first function with delta 2. So when you differentiate with this with delta 2 is here. So the cos of angle is nothing but sine, and because cos, differentiation of cos is minus sine, but because there's a minus here, it will become plus. So this everything will be same except it will be sine. So I get y21 v1 v2 sine of theta 21. So let me write it like this, into sine of theta 21 plus delta 1 minus delta 2. So everything is same, just this cos becomes sine. Now again differentiate the first function with respect to v2 as a variable. So I'll get y21 v1 cos of theta 21 plus delta 1 minus delta 2. So of course differentiation of P2 is 0, so we'll leave it as it is. Now come to this. What is the differentiation of the second function with respect to delta 2? So delta 2 is here. So differentiation of sine is cos. So but then because there is a minus sign, that minus sign will cancel this minus sign. So I get y21 v1 v2 cos of theta 21 plus delta 1 minus delta 2. So this is one expression I got. Here there is no delta 2, so this is constant, and then this is also constant, so there will be zeros. Now differentiate this function with respect to v2 now. So in this term v2 is only the one single is there, so the coefficient of v2 I'll write it, that is minus y21 v1 sine of theta 21 plus delta 1 minus delta 2. Here 2 v2, so v2 square is 2 v2, so 2 y22 v2, so this will be plus, and the differentiation of q2 is 0. So now I got the Jacobian matrix also. So everything that is needed to solve I have on the screen right now. So simply the new values, so the delta 2 v2 is nothing but old values of delta 2 v2. So this is n plus 1 iteration is equal to nth iteration minus f of that is this. So I define it as a matrix fp2 fq2 divided by Jacobian matrix. So this is what is my NR method. So let's implement this using our MATLAB, and then we'll solve it and then find out the values for our system that is given above. So this system.